Students, so we were enjoying the aesthetics of solid state chemistry, the most beautiful crystals you have seen yesterday. In today's class, we will just quickly recapitulate what we have learnt in yesterday, previous class, so that our progress will become more clear. So, in our previous class, we were thinking of crystal systems, and as you all remember, we have got a unit cell, that also we have seen in a lattice how it is distributed in 3-dimensional way. Each unit cell is defined like this with length, breadth and height, with angles between the planes we have seen. That is a unit cell, and among the unit cells we have got two major varieties. One is primitive, the others are centered. It is like this. Primitive means only corners. Just to recapitulate, I am giving again. And centered are of three varieties. You have got face centered, where you will have atoms on faces and corners, and you have got body centered. The molecules or whatever the particles, I can say repeating particles, are present at the corners and the body center position, and the other one is end centered. The end centered will have corners and faces. So, just see the primitive cell has got only the corners, and when you think of face centered, has got corners and faces covered with particles. You can see body centered with corners and that is end centered, corners and opposite faces. So, the difference between end center and face center is simply, in end center only one pair of opposite faces will have atoms. So, this is how we have got unit cells. Later, we have seen some table of crystal systems in our previous discussion by means of some very good names. Cubic crystal system with A is equal to B is equal to C, alpha, beta, gamma, same 90 degrees. In cubic crystal system, you have got three varieties of unit cells. So, that we have done. Then we appreciated tetragonal, where A, B not equal to C, these three angles are same. There you have got two varieties of unit cells. Then we switched over to orthorhombic, the only crystal system which has got four varieties of unit cells. In orthorhombic system only A, B, C are different, alpha, beta, gamma will be 90 degrees. The other day we compared it with a matchbox, and this particular system has got all the four varieties of unit cells. Now, coming to monoclinic. In monoclinic system, the lengths will not be same, and the angles will be, two angles are 90, one is not 90. You have got both primitive and end centered. All these things you should get by heart. In hexagonal system, you have got two lengths same and one is not same, two angles same to 90, one is 120. And in triclinic, all the lengths are in the rhombohedral, lengths are equal, angles, two angles are equal, but the third angle is not equal to 90, you will have only one primitive. In the triclinic, the lengths will be different, angles will be different than 90, that also has got a primitive unit cell. So, overall in our previous class we appreciated all of them, and also this particular fact you should remember that one different systems have got different number of unit cells, especially the last three, hexagonal, rhombohedral and triclinic have got only one unit cell. Orthorhombic has got maximum number of unit cells 4, and our cubic has got 3. So, this also we appreciated. Later we have gone system by system. In cubic system you have got 3, we call them Bravais lattices. In cubic crystal system you have got 3 varieties of unit cells. Of course, we have already seen this. You have got face centered, body centered, you have got end centered, primitive in cubic. In tetragonal you have got 2 unit cells, they are only body centered. Of course, you have got primitive, you have got body centered. Only 2 are possible in tetragonal. In orthorhombic you have all varieties of unit cells. So, end centered you have face centered, you have got body centered, you have got primitive. This is the story of orthorhombic system. And in monoclinic system you have got end centered is there in monoclinic system, end centered unit cell is possible, and you have got primitive. In hexagonal system you have got these parameters, one angle is 120. So, you can see that 120 angle is there, it is hexagonal, a part of it is drawn here, that is primitive of hexagonal. So, coming to the next system, rhombohedral has got ABC, alpha, beta, gamma. Actually you can review the entire video, recorded video to understand, or you can make a note of it. So, better you learn it by heart. So, you have got only primitive here. In triclinic also you have got only 1. So, dear students, these are the crystal systems you have seen, and 14 unit cells also you have seen. But for further study we are going to learn cubic crystal system as well as hexagonal crystal system to some extent. We can understand the unit cells and their parameters very interestingly, provided you understand some close packing of spheres. We take hard spheres and try to arrange those hard spheres in different possibilities of 3-dimensional arrangement. From those arrangements we will understand something. Based on that we will try to establish some unit cells, varieties of unit cells, some parameters. Actually, before exactly going into the close packing of spheres, you may ask me why spheres, why close packing. It is almost like, suppose you take a basket and put 2000 cricket balls and shuffle. The balls will take their own optimum arrangement in order to utilize the minimum possible space. So, most of the space will be utilized, but some unavoidable space wastage will always be there. Suppose you take some spheres and shuffle in a basket, between spheres there will always be some space wasted. So, based on those things we will try to take an analogy to the crystal structures of chemical substances. So, to clearly understand the crystal structures of chemical substances, we first observe some close packing of spheres, how much space is there in between, what varieties of spaces are developed, all those things we will try to understand. Actually, before going to that, I advise you to go through some logical approach towards unit cells and all, so that you will have a better idea on close packing systems. For that sake, I would like to make an attempt to first teach you certain parameters, certain calculations pertaining to the unit cells only in cubic system. As I told you, the simplest system in the all the crystal systems is cubic, because it has got A, B, C are same, alpha, beta, gamma are same with 90 degrees. And also in cubic crystal system we have got 3 varieties of unit cells: primitive, body centered and face centered. So, let us dedicate this particular session to clearly understand various aspects about the 3 unit cells present in the cubic crystal system. Before going to that, let me first remind you one point which I have already discussed in your previous session. Suppose you have got a cubic unit cell, that unit cell is there. See, there are how many varieties you are seeing here? 4 varieties of placements of the spheres. One sphere is at the center. This sphere completely belongs to this unit cell only. If you carefully see this, see, this is at the center of the cube, that totally belongs to this unit cell, hence its contribution has become 1. What does that 1 represent? That is the contribution of the sphere to this unit cell. Means what? This unit cell can count 1 out of this sphere. If you see that green one, you are having only half contribution. Why you should count only half from that? Because in my previous lecture, as I discussed, see this face is there for the other unit cell also. So, if you put a face center atom or sphere, this is shared by both the unit cells. So, for this unit cell you have to count only half, the remaining half is for this unit cell. That is how you should always count only half whenever you find a face center atom, that is why it is showing half here. If it is present in the body, it completely belongs to that unit cell, you can just count it as one atom per unit cell. So, a body atom's contribution per unit cell is 1, a face atom's contribution per unit cell is half, that you should always remember. Now, you see the edge. See, if you take the edge of a unit cell, this is common for 4 unit cells. I am just reminding you, this is the one. Now, check that particular sphere which is present on an edge of a unit cell, that is common for 4 unit cells. So, how much this unit cell can take out of it? Only 1/4. So, the contribution of an edge sphere will be just 1/4 to a particular unit cell. Now, what about the corner? Suppose you take a corner, this is a corner atom. This is common to how many unit cells? This red shown with red is belonging to 1 unit cell, 2nd unit cell, 3rd unit cell, 4th. For all the 4 this is common, and I told you many times a lattice is a 3-dimensional pattern. So, before this you have 1, before this you have 1, this you have 1. So, there are 4 more unit cells for which even this is the corner. So, there is a common corner for 8 unit cells. So, for this you have to count only 1/8. That is the reason whenever you have a common corner ion, you have got 1/8 contribution for the unit cell. So, this particular logical approach will help a lot in making many calculations. I will just try to make you understand some few fundamental calculations what we will do in crystal lattice systems. Suppose I have got a unit cell like this. This is a cubic unit cell. Suppose I have got a sphere here, a sphere here, and corners. Now the question is, how many atoms are there? All are identical. How many atoms are there in this unit cell? How should we understand this? Very simple. See, you just find the atoms in the corners. All the 8 corners have got 8 atoms. Just now I told you a corner atom should be taken as 1/8. So how many corners are there? 8 corners. So 8 into 1/8 makes 1 atom. Don't count 8, 1 atom is there, and on the faces you are finding 2. What is the contribution of face? Half. This half. There are 2 face center atoms. Each face center atom contributes half. So 2 into half, 1. Total 2 atoms. So in this unit cell, how many atoms are there? If that is the question, the answer is 2. Face contribution is half, 2 faces. Corner contribution is 1/8. 8 corners you have got atoms. So 8 into 1/8. So I advise you not to count physically. 8 are there in the corners, 2 are there in the faces. Therefore, there are 10 atoms is a wrong calculation. The correct calculation is 8 into 1/8, 2 into 1/2. I will give one more example. Suppose I have got a unit cell like this, cubic unit cell. There is a body center atom, there are 2 opposite edge center atoms, and you have got 2 opposite corners. That there ends the matter. For logic purpose I am giving this. Don't think there will be a substance with this kind of unit cell, just for logic sake. So how many atoms are there? If you observe this, this is in the body center position. So you have to take 1 out of it, and this is on edge, this is also on the edge. Edge contribution is half, 1/4. So this is 1/4, this is 1/4, 1/4 and 1/4, and it is in the corner 1/8, corner 1/8 as per that reference. So how many atoms are present? 1 plus 2 into 1/4 plus 2 into 1/8. So you should say 1 plus, how much is it? 0.5 plus 0.25, 1.75. There are only 1.75 spheres per unit cell. So this is how one has to calculate. Just see this. There is another cube. You have got atoms on the corners, and you have got different variety of atoms on the faces. Another variety of atoms on edges, all edges. Just for the sake of calculation fun I am giving all this. Don't think there will be a unit cell, some chemical will be having this unit cell and all, just for calculation sake. Now let us assume the black balls, the black one is A. Let us assume the red one is B. Let us assume the green one is C. Now my question is, what will be the formula of this unit cell? Now let us see where are the black spheres. The black spheres are present in the corners, 8 corners. So 8 into 1 by 8 are A. Where are the red spheres? On the faces. Face means what is the contribution? Half. So 6 faces. 6 into half, 3 B's. 6 halves are 3. So B's are 3. Where do you find those green ones? The green ones occupied all the edges. What is the edge contribution? Half. No, edge contribution 1/4. 1/4. There are 12 edges. So 12 into 1 by 4. Again 3. There are 3 C's. So what will be the formula of this unit cell? A, B3, C3. Why I gave this exercise? Just to make you warm up on how to take the contributions of various atoms present at various lattice points in the crystal. So I advise all the students get this by a casual habit. Corner atom 1/8, face atom 1 by 2, edge atom 1/4, body atom 1. So like this you have to count upon the number of atoms per unit cell. Now let us switch over into a very important aspect of cubic system and some important calculations that we will do it now. Cubic system. So you all are aware of the fact it is described by A is B is equal to C, alpha is beta is equal to gamma is equal to 90 degrees. So this is a cubic crystal system, and we have already thoroughly discussed repeatedly that cubic crystal system has got 3 varieties of unit cells. What are they? Primitive, you have 3 varieties: primitive, body centered, face centered. We have got 3 varieties of crystal systems, right? Unit cells. Now let us dedicate this class to clearly understand various parameters pertaining to these 3 varieties of unit cells. Remember one thing, all of them are cubic system, means they all satisfy these conditions. The angles are 90, the faces are all, lengths of all the sides are identical because it is cubic system. So let us now take up one by one and try to study certain interesting aspects of those unit cells. The first one is primitive. Primitive unit cell. In primitive unit cell, what do you have? A cube, you have a cubic system. This is a unit cell. Primitive means only corners. Let me tell you one thing very clearly. This is a blown up model. Means what? For us to understand the relative positions of atoms, we draw like this. In the crystal you will not have these lines and all. Those lines are drawn only to tell you the relative positions of the spheres. So actually in the crystal, how do they exist? I will just draw this face outside. This I will draw outside. It looks like this. So, this only we have broadened like this in order to understand the structure clearly. So, by seeing this, what do you understand? In every phase, the phase diagonal atoms are not in contact, but adjacent atoms, the corners are in contact. Suppose this being a cube, all the edges are of same length. Everything is of same length. So, hereafter we are going to call the edge length of the side length of the cube as A. Now, in the side what do you have? The centers of the spheres. The centers of the spheres are connected through that. The spheres are in contact. See? So, this distance is nothing but A. The distance between the centers of the spheres will make the edge length 0.1. So, then immediately we can say this is nothing but the radius of one sphere, one more radius. Let me call the radius of sphere as capital R. How many capital R's are you seeing there? For this sphere 1 R, this sphere 1 R. There are 2 capital R's, means 2 radii will make the edge length. So, A is equal to 2R. This is a very important relation you should always derive out of any unit cell. This being a primitive unit cell, in this the edge length is given by 2 radii of the atoms, 2 radii of the spheres. This is one aspect we derive. One more point, actually this is a relation between what? Edge length of the unit cell and the radius of the sphere which is making the unit cell. One more thing, how many atoms are present in the unit cell? In this particular primitive cubic unit cell, what is the number of atoms per unit cell? Just now I told you, do not count physically and tell me that it is having 8, no, because they are present in the corner. In the lattice, this is a part of the lattice unit cell, there are other lattices also. So, the corner atom will pick up only 1/8 contribution. So, you have got only atoms in the corners. How many corners are there? 8 corners. Each corner atom contributes 1/8. So, 8 into 1/8. 1 atom. What do you conclude? One unit cell means just 1 atom or 1 sphere. So, if you have got 1 mole of unit cells, 1 mole of atoms, like that also we can count. That is really good. Now, the most important thing is, see, there is a space wasted and this face will come together, actually these lines will not be there, they are together. So, in between there will be some space wasted. I mean to say wasted means unoccupied, there will be an empty space left. So, how to calculate how much space is wasted in the unit cell? This is a very important and logical aspect. Now, what is the fraction of the part occupied in the unit cell? Who occupies the unit cell? The spheres. What is the volume of the unit cell? A cube, because A is the side length. In that volume, how much volume is occupied? Actually, how many atoms are there in the unit cell? We have already calculated 1. I mean to say only in the unit cell only a part of the sphere will come like this, a part of the sphere comes like this, like this. only parts will come, not completely. Sphere will enter into the unit cell, only parts will come, 1/8 part. If you add up all the 8 1/8 parts, you are going to get one sphere. So actually this unit cell is having only one sphere, one atom per unit cell. So what is the volume of a sphere? 4/3 pi r cube. Now how do you say fraction of occupied in the unit cell? So volume occupied divided by volume of unit cell. Occupied volume divided by volume of unit cell. Volume of unit cell is nothing but A cube. Volume occupied is what? It is equivalent volume for one sphere. One sphere has got 4/3 pi r cube. So what will be F? 4/3 pi r cube, only one sphere, divided by A cube. A is 2r. So r cube and r cube get cancelled. You are going to get 4 pi by this is 2 cube means 8, everything you will get. So upon calculating, anyhow I will give the raw number 0.52 you are going to get if you substitute pi value also. What do you understand from that 0.52? 52% of the space in the unit cell is occupied, 52%. The remaining 48% is empty space in this particular primitive unit cell. So what are the three important points you should remember as per the unit cell analysis is concerned? The primitive cubic unit cell edge length covers 2 radii, that is point 1. Point 2, the number of atoms per unit cell 1. Point 3, what is the fraction occupied? 0.52. Obviously fraction unoccupied, empty space 0.48. So what is the percentage occupied? 52%. What is the percentage of space left? 48%. So this is all about a simple primitive cubic unit cell. Now we will switch over to the next variety of unit cell in cubic system alone. Body centered unit cell. We have already defined what is a body centered unit cell. You have atoms on the corners and you have got atom in the body center position. Again let me repeat, this is only a blown up model. You need to know the description of the unit cell. Who are in contact, who are not in contact, if they are identical spheres. To make this, the body center atom will be in contact with all the corner atoms. So actually the corner atoms will not be in mutual contact, but the body center atom will be in contact. If I draw it in a more magnified form, see there is a body center atom which will be in contact with the corner atoms. So the body diagonal covers one radius, one more and one more. Means 4 radii of the spheres cover the body diagonal. And how to calculate the body diagonal length? How to calculate the body diagonal length? In any cube, if you draw a cube, simple Pythagoras theorem. See, this is A, this is A, this length is A and this length is A. What is the length of this face diagonal? Length of that face diagonal is, use Pythagoras theorem, A square plus A square is the square of the length. So, 2A square. So, the length is root 2A. Root 2A is what? The length of the face diagonal. Now, I would like to know the body diagonal length. I mean this length. How to calculate that? Very simple. This is on the bottom and this is A, height, because all sides are of same length, and this is 2 root 2A, this is A. What is this? Let us think this is x. So, x square Pythagoras root 2A whole square plus A square, that gives me 2A square 3A square. So, x is equal to root 3A. So, what is the body diagonal length? Root 3 of the edge length of the unit cell. So, be very clear, once you have a cubic unit cell, if the edge length is A, the body diagonal will be root 3A. All these things one must keep in mind while solving problems in solid state chemistry. You require everything. That is why I am using my own diagrams and logic, so that you can clearly see and understand the approach, everything. See, the body diagonal is root 3A. It is covering how many radii? This sphere is in the corner, this sphere is in the corner, this sphere is in the middle, body center. So, complete diameter of the middle sphere, radius of that corner sphere, radius of this corner sphere. So, there are totally 4 radii. 4 radii is covering root 3A. So, what is the relation? Root 3A covers 4 radii. So, A is equal to 4 by 3 root 3 R. This is all about body center cubic. The relation between the edge length of the unit cell and the radius of the sphere. You keep anything, football, cricket ball, whatever, in a body centered manner, 4 by root 3 into radius of that ball gives the body diagonal length, that is root 3A. Root 3A being 4R, A is equal to 4 by root 3R. First relation we have already got. I told you, just I will remind you again, once you are analyzing a unit cell, we must know the relation between the radius of the sphere, who is making the unit cell, and the edge length of the unit cell. All edges are of same length because it is cubic system. So, in primitive unit cell, A is equal to 2R. In body centered unit cell, A is equal to 4 by root 3R. This also you must remember. Now, what is the next calculation we have performed? Number of atoms per unit cell. In body centered cubic system, what is the number of atoms per unit cell? I taught you many times how to calculate. See, this is a unit cell. Where are the atoms present? One atom is at the body center position and 8 atoms are in the corners, and corner you cannot count as 1. 8 corners, 8 into 1 by 8. So, this is only 1/8 contribution. Therefore, number of atoms per unit cell 8 into 1 by 8 plus 1 into 1. What is that 1 into 1? This is 1. The body center atom 1, 8 corners, 8 into 1 by 8, that is also 1. So, 1 plus 1, there are 2 atoms per unit cell. What else should we calculate in this particular unit cell case? We have to calculate packing efficiency. Packing efficiency means packing fraction. So, in this unit cell, how much fraction is occupied by the spheres? This is also a simple logic, volume occupied by volume of the unit cell. Volume of unit cell is nothing but A cube. Occupied volume is what? How many spheres are there? Each sphere is 4 by 3 pi r cube into number of spheres. How many spheres are there per unit cell? 2 spheres. What is the volume of one sphere? 4 by 3 pi r cube. 2 into 4 by 3 pi r cube is volume occupied by A cube. That we will work out now. See 1, 1/8. So, 2 atoms, 2 spheres. So, volume fraction is nothing but volume occupied by volume of unit cell. So, occupied volume, there are 2 atoms, 2 into 4 by 3 pi r cube divided by volume of the unit cell is A cube. A is nothing but, we have already proved, 4r by root 3. So, 4r by root 3 whole cube. R cube and R cube will get cancelled, and if you work out with the numbers present there, we are going to get 0.68. What do you understand? 68% of the space is occupied in the unit cell, the remaining 32% is a empty space in the unit cell. What about in comparison with the primitive cube, what do you say? In primitive cube 52% occupied, 48% remained unoccupied. So, this is a better occupancy. A body centered cube has got more occupancy. 68% occupancy is there in the body centered unit cell. So, similarly in the same manner we will try to work out for face centered cubic lattice. Unit cell. Again let me tell you, this is a blown up model. This is a blown up model. You have got all the corners occupied, top face, bottom face, left face, right face, back face, front face. This is the unit cell. And what is its description? Without knowing the description of unit cell, we cannot do anything. We can't do any calculations. In this who are in contact, you have got 8 corners, atoms in 8 corners, and you have got atoms in the 6 faces. If I draw this face outside, how will it appear? If I draw it outside, I am going to see something like this. See what happened. These 4 are the corner atoms. This is the face center atom. So what do you understand? In the face, all the corner atoms are in contact with the central atom, and the corner atoms are not in mutual contact. There is no contact between the corner atoms, there is a gap, see, there is a gap. But who are in attachment? All the corner atoms are in attachment with the face center atom. This atom is in contact with all the 4. They are not in mutual contact. So from this what can you conclude? This is what? Face diagonal. And what is this? Edge length. This is also edge length. This length is A, this length is A. So what will be the length of face diagonal? Let it be x. You can use Pythagoras theorem. A square plus A square, x square implies x is equal to root 2a. So the face diagonal is root 2a. This is face diagonal, sorry, till here. This length is root 2a. This is covering R, R, R and R. There are 4 radii of the spheres covering the face diagonal. So what can you conclude? Root 2a is equal to 4r. Root 2a is equal to 4r. Face diagonal covers 4 radii. Therefore, a is equal to 2 root 2r. In every unit cell I am deriving the same thing, similar thing I should say. In primitive cube, the edge length is given by 2r. The body centered cubic, the edge length is given by 4 by root 3r. In face centered cubic, edge length is given by 2 root 2r. Now what else is left? Number of atoms per unit cell are how many? This calculation we have been doing almost for many times. Number of atoms per unit cell. How many atoms are there in the corners? 8 atoms. 8 into 1 by 8, 1. On the faces, you have got 6 atoms. See, on the left, right, top, bottom, back and front. Each face has got an atom. 6 faces. What is the contribution of one face? Half contribution. So 6 into half. 3. So total 4 atoms per unit cell. Do you appreciate the gradation? The primitive unit cell, per unit cell there is only 1 atom. In body centered unit cell, per unit cell there are 2 atoms. In the face centered unit cell there are 4 atoms per unit cell. Primitive 1 atom per unit cell, body centered 2 atoms per unit cell, face centered 4 atoms per unit cell. So this is the story, but now what else is still left to calculate? Packing efficiency. Just recollect, what is the packing efficiency in primitive cube? 0.52, 52% occupied, 48% unoccupied. In body centered cubic, you have got 0.68%, we have already proved. I hope you are writing all this. In case you are not writing, just go through the recorded version again and see how I am deriving. You also practice to derive and then work out the parameters. 68% is occupied in body centered cubic. Now coming to face centered cubic, what is the occupancy we will have to calculate. How to calculate? Occupied volume by unit cell volume. Occupied volume means how many spheres are there per unit cell. There are 4 spheres. So 4 into 4 by 3 pi r cube by volume of unit cell A cube. What is A? 2 root 2 r. A cube we want. 2 root 2 r whole cube. R cube get cancelled. And if you just work out everything, you are going to get 0.74. There is 74% occupancy, which is better. Face centered cubic lattice is the best in the cubic crystal system as per occupancy is concerned, most tightly packed. So the space occupied is 74% in the unit cell, the remaining 26% is a vacant space. So this is the entire analysis of only cubic system. So we will all keep everything in one simple table and we will enjoy. Unit cell A versus R, number of atoms per unit cell, packing fraction. I advise all the students to remember this thoroughly. This is for only cubic crystal system. If it is primitive, A versus R relation is what? A is equal to 2R. The edge length is given by 2 into radius. There is only one atom per unit cell, 8 corners, 8 into 1 by 8, 1. And I have already proved the packing efficiency, 0.52. You can say 52% occupied. Coming to body center cubic, A is given by 4 by root 3 r. And how many atoms are there per unit cell? 2 atoms, 8 corners, 1 atom, 1 body center, 1 atom. So 1 plus 1, 2. And what is the packing efficiency? We have already calculated 68, 0.68. You can say 68%. Face centered. Face centered, A is given by 2 root 2 r. Each face is related to the radius of the sphere as 2 root 2 r. And number of atoms per unit cell, 4. We have seen 8 faces, 8 corners, 8 into 1 by 8, 6 faces, 6 into 1 by 2. Put together 4 atoms per unit cell. And this is going to be 0.74, 74% occupancy. That has got the best occupying space. So all these parameters a student is supposed to clearly understand, and the placement of spheres in the unit cell and their description, everything one is supposed to learn. Just to consolidate this concept, we will analyze few nice examples, maybe I can say for problems kind of a thing. Suppose I say how many unit cells can be made from 1 mole of atoms in FCC manner. If such question is asked, some of the students generally ask, I have got n atoms, 1 mole of atoms. 1 mole of atoms means I have got this many atoms. What is he asking? How many unit cells can I prepare? What kind of unit cells? FCC. Immediately what should you get into your mind? FCC unit cell means there will be 4 atoms per unit cell. Every time you need not draw this, that should keep on ringing in your mind. 8 corners, 6 faces, FCC unit cell. 8 corners, 8 into 1 by 8, 6 faces, 6 into 1 by 2. So, total 4 atoms per unit cell. Using 4 atoms, I can make 1 unit cell. Using n naught atoms, how many unit cells can I make? So, 4 atoms can produce 1 unit cell. I have got 1 mole of atoms, means Avogadro number of atoms. How many unit cells I can produce? So, n naught by 4. As simple as this. Very simple calculation. Now, suppose there is a metal m grams of a metal is there. That metal is crystallized in both 2 different experiments. It is crystallized in BCC unit cells and FCC unit cells also. So, what is the ratio of number of unit cells? That is the question. M grams means m by m moles. So, grams are converted into moles. M by m into n naught atoms, where n naught is Avogadro number. M by m moles, 1 mole is Avogadro number, m by m into Avogadro number is the number of atoms. And this many atoms in one experiment forming BCC unit cells, in the other experiment the same number of atoms are forming FCC unit cells. In which case, what is the ratio of the number of unit cells? Very simple logic. We will call this number as some n. With that n atoms, how many BCC unit cells can you prepare? 2 atoms can make 1 BCC unit cell. N atoms can make how many? So, n atoms can give n by 2 BCC unit cells, body centered cubic. Try to understand the logic. 2 atoms can make 1 unit cell. You have got n atoms in x grams, that will make how many unit cells? N by 2. But to prepare FCC unit cell, 4 atoms can give 1 unit cell. You have already seen 4 atoms can give 1 unit cell. This many atoms can give how many unit cells? So, what is the ratio? Simplest calculation. This is all based on the number of atoms present per unit cell. Now let us go through one more interesting calculation. I have 1 mole of FCC unit cells. I have got 1 mole of FCC unit cells. By dismantling all the unit cells, dismantling means by separating all the unit cells, how many BCC unit cells can you get? Very simple, these are FCC unit cells. One unit cell will have 4 atoms. You have got N naught unit cells. So, how many atoms are there? 4 N naught atoms. Using those atoms, how many BCC unit cells can you prepare? One BCC unit cell carries 2 atoms, you have already learnt, 1 body and 8 corners. So, one BCC requires 2 atoms. So, 2 atoms can make 1 unit cell. You have got 4 N naught atoms. How many? 2 N naught. You can, if you break down N naught FCC unit cells, if the crystal is again recrystallized in BCC form, you can get double the number of BCC unit cells. Obvious. To make an FCC unit cell you require 4 atoms, to make a BCC unit you require 2 atoms. Let us see one more aspect. Actually, like this we can always work out. Suppose I say edge length of FCC is 2 angstroms. Okay, let me say 4 angstroms. Edge length of FCC is 4 angstroms. What is the radius of the sphere making that particular FCC? Such questions are quite common. Suppose we know that A is equal to 2 root 2 R, where R is the radius of the sphere making the FCC. This rule is for only FCC. So, R is equal to, edge length is given as 4 angstroms, 4 by 2 root 2. This goes 2 times root 2. As simple as this. And I told you one thing, in FCC unit cell, the face looks like this. Did you understand that some space is not occupied? Some space is unoccupied, length is there. I will give a very logical question on this. How much length in an FCC unit cell is not occupied? How much length of the FCC unit cell, edge length, is remaining unoccupied? He is asking the percentage of unoccupied length of the edge. How to work out that? See, this length is how much? A. Out of A, some space is not occupied, some length is not occupied. What is occupied? R on one side, R on the other side. Means 2R is occupied. What is the total length? A, 2 root 2 R. A is equal to 2 root 2 R. Out of 2 root 2 R, 2 R is occupied. So, subtract. So, unoccupied length 2 root 2 R minus 2 R will give me how much? 2 R common, root 2 minus 1. So, 2 R into 1.414 minus 1. So, 2r into 0.41. What is this length? This is unoccupied length. See, try to understand. 2 root 2r is total length. 2r is occupied length. The left out length is how much? 2r into 0.41. So, what is the percentage unoccupied? That is the question. What is the percentage length unoccupied? So, unoccupied length divided by total length 200. So, that gives me 2 to cancel 0.41, or you can say 41 by root 2 percent is unoccupied. As simple as this. See how many nice logical questions we can work out based on simple cubic parameters. So, a student is definitely supposed to know the clear view on the unit cells in every crystal system. Of course, in your syllabus you have got only cubic system and hexagonal system, that we are going to understand very clearly by observing the close packing of spheres. What do you mean by close packing of spheres? Suppose I want to arrange so many spheres of identical radius. Suppose I have got spheres like this. So many thousands of spheres I have got. I would like to arrange them in a 3-dimensional manner. So, first I will keep a single layer of that. A student will arrange like this simply. But one more student will arrange in a different manner. See, there is a difference between this and that. This is like, if you connect the centers of the spheres, you will get a square kind of a thing, but there you can't have such scope. And if you again keep one more layer on this, you will get cubes, but there you can't keep like that. So, in this what are you getting? If you connect the centers of the spheres, you are getting hexagons. So, with a simple one layer system itself you have got two varieties. If I go for second layer, if I go for third layer, I will have many different possibilities of 3-dimensional arrangements of hard spheres. If you can understand the close packing of spheres clearly, we can transform those arrangements as an analogy to understand various crystal structures. First, this is an easy method to understand the possible arrangements of the spheres. If you understand that, we can extrapolate this logic for various crystal structures. What are the possible crystal structures we can come across in solid state chemistry, and we will adopt those structures for different ionic crystals and covalent crystals and some substances, then we will study them very carefully. So, this class I have just dedicated to make you understand the contributions of spheres to unit cells and the number of atoms per unit cell in cubic crystal system in all the three varieties of unit cells. We have also seen the number of atoms and length versus edge length versus radius relations. We have also appreciated the packing efficiency in primitive cube, body centered cube, face centered cube. We will have to learn the density of unit cell also, which we will do it in the next coming classes. So, I advise all the students to repeatedly go through the lectures and make your own idea on the subject, make a notes of it, take some pauses and take notes and work out so that it will become very easy for you. Thank you. We will meet in our next lecture.